We are on section 19.8, converting mass to energy. So we talked about nuclear fission last week and the tremendous amount of energy that gets released when you split an atom. Where is that energy coming from? Because it has to come from somewhere, right? So here is the fission reaction for uranium-235. You bombard it with a high-energy neutron. It splits into barium. There's a typo. That's not barium-14. That would not work. Barium-140. Just left out a 0. It's right down here. Okay, and krypton-93 and 3 neutrons. Well, let's look at the masses involved here. If we add up the mass of the reactants, and notice here we're using more significant figures than we usually do. The total mass of reactants is 236.052585 atomic mass units. Total mass of products, 235.86769 atomic mass units. Not the same, right? No. There's a problem, right? What happened to the law of conservation of mass?
That's
only in chemical reactions. This is a nuclear reaction. In nuclear reactions, matter can be turned into energy and vice versa. So this is that exception thing. So in nuclear reactions, matter can be converted into energy. The tremendous amount of energy that comes out of this is because there's some matter that disappeared. So this is where Einstein's famous equation E equals mc squared comes into play. E is energy that is produced, m is the mass that is lost, and c squared is the speed of light squared. So we can actually calculate the amount of energy produced when one atom of uranium-235 is broken apart. So the way we would start this is we have to compare these two masses. So the difference between those is the amount of mass that has been lost. So I took the liberty of doing this on paper so that it would go a little faster. But then again, maybe not if I can't seem to push any buttons. Oh, my goodness. It's just, it's one of those days. Oh, it's purple today. It's just, there's this layer of kid sticky greasiness on my iPad screen. So the mass lost equals the difference between those two masses. So it's 0.18489 atomic mass units. Now that is not a lot of mass, but the speed of light squared is a really big number. So what we need to do is we need to convert this to kilograms, and so you need this conversion factor, which is in your book somewhere. 1.66054 times 10 to the minus 27 kilograms is equal to 1 atomic mass unit. An atomic mass unit is just ridiculously small. So atomic mass units cancel out. And so the mass is, what is it? 3.0702 times 10 to the minus 28 kilograms. You're like, oh, well, he just lost a little bit. What's the big deal, right? Well, put that into this equation, E equals mc squared. So here we've got the mass, kilograms. You know what the speed of light is? 3 times 10 to the 8th meters per second. So we're going to use more sig figs. 2.9979 times 10 to the 8th. That's not a very good 10 to the 8th. Let's try that again. Meters per second, and that's squared. A kilogram meter squared per second squared is also known as a joule. And so this comes out to be 2.7593 times 10 to the minus 11 joules. Well, that's not very impressive, is it? That's for one atom. What if we had a mole of atoms doing this?
Whoa.
Do the math.
Okay, so that's joules per atom. How would we find per mole? Avogadro's number. 6.0221 times 10 to the 23rd atoms per mole. And the atoms cancel out. And this ends up being, I'm going to put it into kilojoules, which doesn't really help much, but 1.6617 times 10 to the 10th kilojoules per mole.
Okay,
That's approximately 17 billion kilojoules per mole. That's a lot of energy. How much does 1 mole of uranium-235 weigh? 235 grams. That's less than the mass of a can of soda. That's a lot of energy. Comparing that to exothermic chemical reactions, a highly exothermic chemical reaction will give off about 1,000 kilojoules per mole. 17 billion. So little bit of matter gets converted into a lot of energy. So that brings us to a concept called mass defect. Let's look at the formation of a stable nucleus from its components. Helium-4 is a stable nucleus of helium. So if you combined 2 hydrogen atoms and 2 neutrons, that would get you a helium-4 atom. Okay? So here are the mass totals for the reactants, the mass totals for the products. Again, mass is not being conserved here. The helium-4 atom has less mass than the sum of the masses of its components. This is called the mass defect, and it exists in all stable nuclei. So we could figure out how much energy that corresponds to as well. That the energy related to that mass defect, the calculation we just did with the uranium, E equals mc squared, that amount of energy is called the nuclear binding energy. And it's equivalent to the amount of energy that would be required to break apart the nucleus into its component nucleons. Remember, nucleons are protons and neutrons. We don't usually express this in joules or kilojoules. Nuclear physicists prefer electron volts or mega electron volts as needed. An electron volt is the kinetic energy of an electron that has been accelerated through a potential difference of 1 volt. Very creative name there, electron volt. Take 1 electron, give it the energy through a potential of 1 volt, and that's what you've got. So a mega electron volt is 10 to the 6th electron volts, and that's equivalent to 1.602 times 10 to the minus 13th joules. So a mega electron volt sounds big and impressive, but it's actually very small. Using E equals mc squared, we can come up with a relationship between 1 atomic mass unit and mega electron volts. And that's this guy right here. 1 atomic mass unit is equal to 931.5 mega electron volts. This is a very useful conversion factor. Because in that previous problem with the uranium, instead of pulling out Einstein's equation and getting out the speed of light, we could just use this and calculate the energy in electron volts. So what is the mass defect for helium-4? It's 0.03038 atomic mass units. So what does that make the nuclear binding energy? Well, we can do this then just using dimensional analysis. So 0.03038 AMUs. We have that relationship that there's 931.5 mega electron volts per atomic mass unit. So that gives us 28.30 mega electron volts. That's the binding energy for a helium-4 nucleus. The binding energy, though, is going to depend a lot on how many nucleons are being bound together. And so they'll often calculate a binding energy per nucleon so that you can compare different nuclides. And how can you compare helium to carbon when carbon is so much larger? So to calculate that binding energy per nucleon, you just take the binding energy, 28.30 mega electron volts, and you divide it by the number of nucleons. How many nucleons does helium-4 have? 4. It's the mass number. Per 4 nucleons. And that gets us 7.075 mega electron volts per nucleon. That lets us compare different nuclides. And what we see is that the larger the binding energy per nucleon, the more stable. So you can compare, say, carbon-12 or carbon-14 with helium-4 and get an idea of which is more stable. Any questions? So this question is asking us to calculate the mass defect and nuclear binding energy per nucleon in mega electron volts for uranium-238, which has a mass of 238.0500784 atomic mass units. So how do we figure out what the mass defect is?
Difference in the mass.
The difference in the mass of the components versus the mass of the actual nuclide, which is given to us. What is in uranium-238?
Hydrogen and neutrons.
Yeah, so we can think of it in terms of hydrogen atoms. How many hydrogen atoms?
92.
92. So uranium has an atomic number of 92. So 92 hydrogen atoms would give us the 92 protons and the 92 electrons that we need. And then how many neutrons are there?
238 minus 92.
238 minus 92. Yes.
It's a number.
It is a number. 238 minus 92. 146. So plus 146 neutrons.
Yes.
So then we need masses for those things, right? Depends on where you look. I'm just going to go with the masses they used in the book. We tend to think of the atomic masses of elements as being like set in stone, but they actually have revised a few of them, and so you'll see some variations in periodic tables. This one says the hydrogen is 1.00794. This one's using 1.00783. Other than variation, what could be the cause of the difference there?
Well, there's different isotopes.
There's different isotopes of hydrogen, right?
Deuterium and tritium.
So we are looking only at the isotope of hydrogen that has no neutrons. So that's 1.00783. So 92 times 1.00783 atomic mass units. And then we've got 146. That's a lot of neutrons. Neutrons are 1.00866. Those are all atomic mass units. So 92 times 1.00783 plus 146 times 1.00866. almost wrote with the wrong end here. So that is equal to 239.98472 atomic mass units. The components for uranium-238 weigh that. The actual uranium-238 atom weighs 238 point that. So we need the difference here for the mass defect. So mass defect is going to be the 239.98472 atomic mass units minus 238.050784 atomic mass units. Now, for an exam, you do not have to memorize the atomic mass of a neutron and a hydrogen atom. That's just dumb. But this isn't an exam, and so we are expected to go look it up. 238.050784. So 1.933936. That's almost 2 hydrogen atoms. Okay, so that's the mass defect. Any questions about that? And then they want nuclear binding energy per nucleon. The easiest thing to do there is to take the mass defect and apply that relationship between AMUs and nucleons. So this is AMUs and mega electron volts. So that was, I've got it memorized now, 931.5 mega electron volts per atomic mass unit. So that gives us the binding energy for one atom, right? But we want per nucleon. So we need to divide by the number of nucleons. How many nucleons in uranium-238? 238. Isn't that convenient? Okay, so times 931.5 divided by 238. 7.569. Yeah, that's about right. Mega electron volts per nucleon. Now that's in the same ballpark as for helium, isn't it? Helium was 7 something. So let's go back and look at that. Oh, you know what? I don't think I can. Never mind. Because I wrote that on there and it has kind of disappeared. But it was done in the book. It was 7.075. So for helium, it was 7.075. For uranium-238, it's 7.569. Which is more stable? The uranium-238. The binding energy is larger. Any questions? If we graph nuclear binding energy versus mass number, we see that the binding energy per nucleon increases dramatically from deuterium down here as we go up to about carbon-12. And it reaches a peak around here, around 60, and then it starts to go down a little bit. And so we find that breaking heavy nuclei into smaller ones is an exothermic process because these are more stable. You take uranium-238, you break it into smaller pieces, it becomes more stable. And we would also expect that combining two lighter nuclei into a heavier one would also be exothermic. And it turns out that it is.